Hi. Today's lecture is going to be the chapter 10. In this lecture, we're going to cover the main topics about chapter 10, which is the phase transformation. We also going to show you some of the homework problem as the example, how you use those ideas that you learn in chapter 10 to do some calculation and some not just calculation, but understand how the phase transformation is going through during the space diagram. So here are the topics. The first topic that we're going to cover is about the kinetics of the phase transformation. There's two stages of the phase transformation, which is nucleation and the growth. So for each one of this is to think about when you melt a metal into liquid. And once you change the temperature, the metal solid solution or the liquid solution will have some transformation. It depends on not only the material, but also depends on how fast or how slow that you are doing this transformation by changing the temperature. So the rate of the change temperature and what temperature that you are starting with and end at, both are going to change how this phase transformation is going to be. So there's several different quantity that will change the phase transformation. We wanted to start with how this transformation is by looking at the two-stage nucleation and the growth. So if you think about the metal being melted, the composition of metal, which is an alloy, that is become a liquid. And sometimes it's not liquid. It could be a solid solution, such as the iron carbon system that you can heat it at the high temperature to be a solid solution. And that is what we call the austenite, right? That's a more stable solid solution at a high temperature. Once you cool it down, then it will go through several different reactions. And one of the things that we most interested previously is the eutectoid. And we're going to see this kind of things happen again because the last part of chapter 10 is going back to the iron and carbon system again. But just by looking at these, nucleation is that you start with all liquid. This is all liquid. Now the liquid composed by initial composition. So you have certain position of iron. You have certain position of carbon to start with. And then it will start to form a smaller particles. That small particles is where you are going to have a nucleation. Okay, so lower the temperature, then you have a small particle. This small particle is not stable. The small particle still will dissolve in the liquid. It's actually it crystallizes at the same time as it dissolves into the liquid surrounded by it. But if you keep on lowering the temperature, then the rate of nucleation will increase, and therefore you're going to form a larger grain. The larger grain or larger particle is the nucleation. Now, how do you change this nucleation? How this will affect the rate of the nucleation? Well, depends on two things, which is the thing that we show you here. The rate of nucleation depends on the free energy, the Gibbs free energy. So if you read the book, they will have a very long description about what these are. The Gibbs free energy is that how fast these things would happen. It depends on how much of the surface area and how big the grain is. So it depends on two different kind of Gibbs free energy. One is the volume, The other one is the surface area. Okay, so 2 gives free energy. For the surface free energy, you can think about that. If you wanted to cut an object into 2, then you're gonna have more of the surface, right? If you start with some small ball and you cut it into 2, then you're gonna have more surface. But how can you make it have more surface energy? You need to provide some work. You have to give energy in order to cut it into have more surface area. So this surface area related to the total area of the sphere, which is proportional to this. The other energy is that if you want to combine smaller one into a larger one to increase the volume, this will reduce the area, right? It's opposite to when you cut it. Now you combine 2 things into 1. When you combine things together, it's going to release the energy. So the when you cut it into small area, you give energy, but when you form a larger volume, you release the energy. And if you wanted to make the reaction happen, you have to have a negative energy, the negative change of energy. So reaction tends to release the energy in that sense. So that's the basic idea how this rate of nucleation is. In the book, they will tell you how you can find those things, which we will not emphasize on this. We wanted to just show you some of the key things that you would do some calculation. So this equation, the 10.1, is the equation to tell you if you have both of the Gibbs free energy happening, then the change, this delta meaning the change of the surface energy is the summation of both energies. So this is the volume, this is the surface area free energy. So volume free energy and surface free energy combination of that is going to be the total free energy change. When they do a solidification, these 2 values will change because when you do solidification, the grain will start to form, to grow. When you have several grain happen, the surface energy increase. When you form a crystal, then you are going to increase the volume, then you have a larger volume, free energy. Then it shows a graph like this. And this graph just shows you how big the grain is going to relate to how much of the free energy change, right? So it determines by the R, which is this R here and this R here. This gamma here, this looks like an R, but it's not R. This is a gamma. The gamma is the surface energy. It's the surface tension energy. It's a positive number. So it turns out the 2 lines that you see here, the red line represent the surface area. And we just told you the surface free energy is a positive, because think about it, need kind of energy goes into the system in order to cut it into smaller pieces to increase the surface area. The bottom line is the volume free energy. This is the one that you want to increase the size, and this one requires, this one will release energy, so it's going to be a -1. So sum these 2, then you will see the combination between these 2 will give you a curve, which is a solid green line in this picture. And there is a point where you have the maximum of the free energy change at this point. And this is the point that we will say at this point, you will have a size of the grain where this size is a minimum size for this one to continue to grow, because the nucleation to grow is when the size of the grain is large enough to be stable. Otherwise, it will dissolve into the liquid again. When the size is larger than that, it will just continue to grow because the reaction will likely to happen spontaneously when the energy will become a negative, because the trend after this is going downwards, is going to be negative. So this is the point that we are most interested to know, how big the size will grow, then we will have a stable transformation growth. So the first few question in your homework asking you to use these two equations to find what is the critical size of the grain and what is the free energy that is required to have these things to happen. Let me just tell you a few things about the symbol in this equation. This delta HF is the latent heat of the fusion. So this is the delta HF. The Tm here is the melting temperature. Okay, it's the melting temperature. The gamma at here is the surface free energy. So melting temperature is this one here. The transformation temperature is where there's the temperature that you transform into. So it's the temperature that you're looking at, and that is the T over here. The change of the temperature is equal to the melting temperature minus the transformation temperature, which is the change of the temperature. And that is the denominator in this equation here. The same way that you can use all these symbols in this free energy expression, which is the change of the free energy that you can use to find that. Now, those just the thing to find those energy and the radius of the grain. But if you wanted to look at what is the rate of the nucleation, then it comes out to be this equation. Now, book also talk about you might have a homogeneous nucleation, you might have a heterogeneous nucleation. Homogeneous nucleation meaning all the things in the liquid or the solid solution, they will start to have the nucleation at the same kind of uniformly. But heterogeneous, they are not. And actually, the normal situation is things will be heterogeneous because you have a faster rate of the growth around the grain, but away from the grain, the growth will be slower. It's not actually very uniform. And if you start with some grain, it will likely to form the grain around those surface. But to make it simple, we use the homogeneous way to look at the problem. This equation is kind of complicated because it depends on several constant here. You can see the K1, K2, and K3. These are the things that I defined here that you can look at by itself. The K1, K3 is represent the number of things. The K2 is a constant, depends on the temperature. The QD here is the same, the Q that you see in the diffusion, that is the activation energy. The K is the Boltzmann constant, and capital T represent the temperature. So you can look at the book to find out each one of these, what are they represent, and just pay attention to their unit as well. If there's a calculation that you need to do, then you need to be careful about the unit. All right. So that is the first one, is the nucleation. So once you have the nucleation, what happens? Once you have the nucleation, and if you keep this at the temperature, the low temperature, then this area here will start to have a larger grain to grow. That is the growth, right? And they grow larger and larger to form a larger crystal inside of this solution. So they grow. And finally, they will become a crystalline. So at the end, they will become a crystalline. Now, how do we make the growth? How do we control the growth? The growth also has a rate. It depends on diffusion. So that's why we introduced diffusion in the chapter 4 and 5. Just try to give you some idea. So when you have impurity in metal, the rate of the diffusion, which is the one that we saw previously, and this is similar to the coefficient of diffusion, right? It depends on some kind of exponential and Q over KT. So this equation is what we call the growth rate equation. The G here represents the growth rate, the rate of the growth. It is the diffusion and is Arrhenius expression. The C is a constant, depends on the material. So you can use this equation to find the solution. This, just to remind you, this actually represent, this is going to be the C times 1 over E Q over K and T. The minus sign make this one to be the denominator in this ratio. So that is how this equation is represented. Okay, now if we combine these two different rays, and then you will come up with this picture at here. The ray at the bottom is 1 over second. And on the x-axis is our y-axis is our temperature. The Tn represent the melting temperature. So if you go lower than the melting temperature, then you will have a solid solution, right? Liquid will become a solid. And if you look at the curve, you can see the nucleation rate will start to increase once you lower the temperature. The higher the difference of the temperature, the faster of the nucleation rate. But if you make it too cold, the nucleation rate will decrease because this rate, or normally higher temperature, is going to have a higher transformation. So when you lower it too low, then it will start to decrease. Then opposed to this one, that we also have a growth rate. The growth rate depends on the temperature. The faster of the temperature, the higher rate of the diffusion. So the growth rate is going to be higher. That's why this one just keep on growing, because higher temperature, higher of the growth rate. And then you combine these two is the overall transformation rate. And you can see this overall transformation rate is not just go up or go down. It actually has a peak at a certain point of the temperature. You're going to have highest of the rate of the transformation. And this is kind of important for us if we want to control how the solid solution to be formed. What is the best combination of these two, or what is the best temperature that you should control in order to get the overall transformation rate the highest? Okay, so that is this graph shows you. Homework 10.3, homework 10.4 relate to the above equation that we just mentioned. There's one question that says supercooling temperature. The supercooling meaning if you cool the object below the melting temperature, and and you look at how the transformation is, that is what this supercooling means. The supercooling temperature is actually the delta. So it is the Tm minus T in the equation 10.7. So when there's a table shows you the delta T for different materials. So when you work on that homework, make sure that you understand the delta T actually is this two difference, is the difference of these two, or the difference of these two. All right, after the discussion about the growth and nucleation rate, we are going to look at the kinetic of the transformation. And the idea is this: because temperature is one of the factors would affect how this transformation is. And time is also another factor. Why don't we just fix one thing, and this time we're going to fix the temperature? Let's say we are transform things at the same temperature and keep that same temperature for a while. I want to see how much of the thing actually transform to certain kind of the type or certain microstructure. And that is actually one of the things that we did in our lab, the hardenability. The rate of the change temperature is going to change how the transformation is. But if we keep the temperature at the same, which means we maintain the same temperature, and the rate of the transformation will depend on this temperature. So the graph over here is an S-shaped graph. So it's high on the right and low at the left. And the bottom part is what we call the time, but it's not only just time, it's a log. It's a log scale. So be careful about the log scale. Some people doesn't really know how to read a log scale. Then you should look back to when we start to talk about the fatigue, that we introduced the SN curve, and we shows you the log scale is different from the linear scale. So you have to be careful how to read those number from the log scale. So this is the graph that we generate by a fixed temperature. So the fixed, say for example, 500 Celsius. And that means if you keep at the 500 Celsius and then you start with the time at here, let's say this is a 0.01 second, and go all the way to the right, this may be like 10 days. Okay, now the scale again is the log scale. If this one is 1, then the next unit will be 10, and then the next same length will be 100. That is what the log scale means. If you look at the middle number between the 1 and the 10, this is not equal to 5. This is approximately equal to 3. So the log scale is they start with a larger distance. Then when the number goes the larger and larger, the distance of the scale will be smaller and smaller. So that's the log scale. Now there's another two equation came from this picture, is that if you have this kind of S shape, then we can actually write the equation like this. This equation is Avrami equation. The Avrami equation tells you how much of the fraction will be formed and will be formed over a certain period of time. So the Y here represents the percentage of the transformation that complete. The T here represents the time. The K and N are the two constant, depends on the type of the reaction or type of the material. So the T is going to be in second. This is going to be the percentage. So if they say, 60% of the transformation will form, that means the Y is equal to 0.60. You can also have a transformation rate. That rate is simply just the reciprocal of the halfway to complete the transformation time. And the halfway transformation time is right here. That means how much time does it take to transform half of the material. And that's the T subscript of the 0.5. Okay, now the homework 10.6 and homework 10.10 are related to the equation, so you can use those equations. Now, when you do this kind of calculation, one of the useful thing that you might to keep in mind is that this equation will help you to relate how can you find the time, because the time to the power of n, where n is normally not constant, it could be like 5.7, 2.9. Then how do you find these? For example, if you say you have 60% of the transformation after certain time, and the time, let's say, is 100 seconds and to the power of n, and then how do you solve this? So usually is easier way to solve this is you take the nature log. So you move this term here to the left and move this one to the right. Then you will have as EK 100 of n equal to 1 minus 0.6 equal to 0.4. And how do you solve this? You take nature log. You take nature log of this side and take nature log of 0.4. And the nature log of this whole thing will give you K 100 of power of n. That equal to nature log 0.4. Right. Now, if you know K or you know n, you can solve the other one. And this is just one of the equation that will help you to solve some situation. So it's actually based on that you take nature log of this expression, that you can simplify this relationship, that you will solve a lot of time. You're going to solve the two equations at two different conditions. Then you can solve for the K and you can solve for the n. All right, the next part of this chapter, we'll look at another picture. That picture is called the isothermal transformation diagram, or the TTT diagram. The idea is coming from here. We just said the transformation rate depends on the temperature, and the percentage of the transformation take time to form the crystal. So if we look at the time, we look at the fraction, it's this picture that you see. And how do we generate this picture? And this picture is for the case that we have eutectoid reaction. Eutectoid reaction is that you start with one solid solution, become two other solid solution, the combination of these two. And it only happens at a certain composition and a certain temperature, right? So if we make this equation, make this transformation to start like this. Let me just quickly draw a portion of this phase diagram. So this is where you eutectoid, and this is your alpha. Here is your gamma. This is your alpha plus gamma. So this point here is where you have the eutectoid, and this composition is 0.76. If you start with this composition, you heat it up to this temperature, then everything is the gamma. That is the stable iron carbon alloy at a high temperature. Then you start to cool it. Once you cool it, let's say I cool it and I just make it super cool at this temperature. This temperature is not the temperature of the eutectoid temperature. It is the temperature lower than that. And let's say this is 675 degrees Celsius. Or you lower to another lower temperature, which is like 600 degrees Celsius. Then you're going to get the graph for each one of them. And we measure like how much time does it take to make a certain amount of the material to be transformed into the perlite, right? So this is what the graph tells us. It depends on the temperature. The higher of the temperature that you wanted to form the solid solution will take more time. The lower the temperature actually transform faster. Okay, so that is the diagram. Now, this diagram is hard to visualize it because you have the temperature is changing, time is changing, percentage is changing, and so it might be easier if we change this diagram to another way. This is the way that we usually represent the changing and in a certain temperature. So we pick one of the line at a time. We draw the line by using this diagram. This is what we call the isothermal transformation diagram. Oops. It is also known as the TTT diagram. The TTT diagram represents the temperature, time, and transformation. So the temperature time transformation diagram is the isothermal transformation diagram, meaning we are looking at the transformation at a certain period of time, and we can make a diagram like this. Starting from now, we are only going to look at the iron carbon system because that is the system that we are most interested and is well studied as well. These diagrams take years to generate because you have to do the experiment over and over again to verify these things, and it takes a lot of time. So how do we read this diagram? The first thing that you look at here is that you notice there is so-called eutectoid temperature. That eutectoid temperature is coming from the phase diagram, where the phase diagram is what we call the equilibrium phase diagram. It is the diagram that you generate when the transformation happen at the very low rate. You don't do like a quench. You make the temperature lower at a lower rate, so that will be the result it will form. The eutectoid temperature at here is 7 27 degrees Celsius for the iron carbon system. If you have the temperature is close to 727, it will take a longer time to complete 100% of the transformation, right? So you can see if you are at this point here, it will take how much time? 10 to the fifth. You take more than 10 to the fifth of second in order to have the 100% completion, because the 100% completion at here it's going to extend much longer until you can reach to this to be finished, right? So this is your beginning and this is your end. So it takes a lot of time in order to make it to the end. Now this picture shows another thing that you might notice. There's a lot of like a familiar words that show up here. One thing that you notice is this austenite. The austenite is the gamma. Gamma is stable at the high temperature. Once you lower the temperature, it's unstable because it's going to transform. So right here, when you lower the temperature to be lower than the eutectoid temperature, 727 degree, you are going to transform that gamma into different things. And what kind of thing it will transform? Well, and it depends on the temperature. So let's say if you start with the temperature at here. Okay, not sure what this temperature is. Okay, this is 675. So you start with the gamma austenite. You lower the temperature to allow the phase to transform. And you keep at 675. Okay, you keep at the 675 to allow it to transform. And how much time does it take to transform? This is the starting time that you start to have the transformation. So this is what they call the begin curve. So it's 0% per light to form at the beginning, but if you keep it at the same temperature over a certain period of time, it will complete 100% of the per light. So the green is 100% of per light, the red line is 0% of the per light. How much time does it take? How do you read that? Well, you look down to the x-axis, you make this one go down to here, this one go down to here, and the bottom part is the time. So you read the time. So this one is 10 seconds. What about this one here? Well, this one is not like a 1.3. It's not 1.2. This one is actually about 20 seconds because this is a log scale. If you have a log scale, if you start with 10, the next big scale is going to be 100. And it's not like the usual linear scale, which is cut into the even space. Usually the first one is about 0.3 length of the whole length. And this will be actually 20, and the next one will be 30 and 40, etc., until 100. So this is about 20. So when you start at the 22nd and you keep it at 675 degree, it takes how much time? Then you have to read the next one, which is this one here. Now again, this one is not to the 1,000, it's above 100, and this is approximately, if you look at the log scale, I would say this one probably is 500. It is like 5 times 10 to the 2. Okay, so about like 500 seconds. So how much time does it take? It's take 500 minus 20 seconds. That is how much time does it take to complete the overall transformation. Okay, so that's how we create this one, which is the TTT diagram. This is the TTT diagram. And if you say, I only allow this one to maintain at a temperature for 100 seconds, if you make it lower to 100 seconds, then you see this is 100 seconds, and you keep it the same rate, you can see it intercept at here. And the dash line here, the dash green line here shows you what this is like a 50% of the completion rate. So that means if you only allow it to cool for 100 seconds, from 20 to 100, that's about 80 seconds, then you can achieve 50% of the fraction will become a solid. And that is what this diagram shows you. So in the lab, we're going to show you some of the example, but let me just show you one of the example that you will do in your homework. So in your homework, out of this will ask you to give an explanation what kind of the material will be transformed after the transformation, given with certain situation. So for example, this one here is a complete TTT diagram. The complete TTT diagram has several symbols on this diagram. This A here represents the gamma with the austenite steel. The P here represents the pearlite. The B here represents another microstructure called the burnite. The N here is called the musternite. So you can see the musternite is at the lower temperature when the steel alloy is cooling at the lower temperature, and most likely they're going to form the musternite. The musternite is a material which is brittle. It's very hard, but it's not practical for use because it's too brittle and it doesn't give you a time of the warning. So we use steel will be a little bit more ductile than the brittle one. The pearlite and burnite, they all have a different strength, which we will show you another picture to tell you the difference between these two. So the boundary between the pearlite and the burnite is going to be the temperature over here. So it's about 530 degrees Celsius. Let's look at how we apply these, and you will see how useful the TTT diagram is. Here we said we have an isothermal transformation for certain composition is 0.45 weight percentage of the carbon alloy. And we use the TTT diagram to show the transformation. And we begin with a 45 degrees Celsius. We keep this temperature for a long time, so everything becomes a gamma. So if you look at the diagram over here, A45 is about this degree. Starting temperature. That just tells you everything is going to be stable gamma. And then they give you a several different process. This process just tell you how they prepare the transformation, how they go through the transformation. I'm going to show you some of the transformation here. Let me just start with the first one here. I'm going to use a color blue here to represent what that is. So the color blue for this one here. The rapid cool to 250 degrees. So you start with this one here, the A45 degree. And the bottom part is the time, right? This is the time. So rapid cool, what does that mean, a rapid cool? The rapid cool meaning that you're going to cool it in a very quick time, and that quick time okay, so let's continue. Let's start with the gamma 845. We are going to rapid cool to 250. So rapid cool meaning you cool it in a very fast way. You can see we start from 0.1 second because it's hard. There's in the log scale, you cannot represent zero. So we just make a very, very small number. So we start with 0.1 second. We're going to cool it very fast. So how do you represent cooling very fast? And we're going to cool it to what? To 250 degree. So where's 250? The 250 is about midway of this. So this is a 250. So we cool very fast to 250. That just simply means, oh, okay, let's just cool it within 1 second, right? So that will make it go to here. And if you cool it to this one, and then what? And then you're gonna hold it for 1,000 seconds. Hold it for a 1,000 seconds, then you quench to room temperature. So hold it for 1,000 seconds, meaning we stop, let's say like 1 second, 1,000 seconds is right around here. This is 1,000 seconds. So you quench to this temperature, you hold it for 1,000 seconds, right? And then you're going to cool it, you're going to quench it go, meaning you go straight down to room temperature, where room temperature is about here. That's the room temperature. So going to quench to here. This is a final point. We start from here and we go with the fast, rapid cool to 250. And then we're going to hold it for 1,000 seconds and we quench it to here. And what is the material? If you look at the path, it starts with gamma, but then you go down to M. The M meaning is the musternite. So it's the musternite, and then it will keep it longer time for it to form this musternite. Then you quench it to hold the composition, meaning your composition is going to be musternite for this process. Okay, but how much the musternite? It's not everything become a musternite. You can see there is a line called the star musternite, 50% musternite, 90% musternite. We're a little bit above that. So in this case, this one is going to be like 80% of the musternite will be formed in this structure. Okay, what about the rest of the thing? Well, the rest of the thing is going to be the untransformed austenite. So you have 80% of the austenite, you have 20% of austenite in this structure. So that's what this process is. Let's try another one just to make sure that you know what this is. How do we do this? Let's try C here. So in the C, I'm going to use another color to represent this. Let's use a green color. So we're going to use green color on this one here. We rapid cool to 400 degrees Celsius. We're still starting from here, and we're going to cool to 400. So 400 is right here. We're going to super cool this one to 400. Once you cool to 400, we're going to hold it for 500 seconds. So 500, where is 500? This is a 100. This is 1,000. The 500 is going to be around maybe here. Okay, so you transform this one, go to 500, you hold it for this one to go 500. So let's go from this place to this place. Okay, so if you go to there, and what do you do afterwards? And you, for problem C, we're going to quench to the room temperature. So we're going to quench this one to the room temperature here. So we start from here. We go down. We wait 500 seconds to here, then we quench down. Okay, now you see there's a dashed line here. The dashed line here represents the boundary between a perlite and the burnite. So that means if you cool to 400 degrees Celsius, it's going to form the burnite instead of the perlite. So this one, you are going to have the material transformed into a burnite. Okay, because the line that we have in here represent how much they transform to which. This one here is the line that you have A and B, which means in this region, you have both the austenite and the burnite, and the green line here represent the border that you are going to have 100% complete of the transformation into the burnite. Everything on the right is 100% a burnite. If you go to the top, this one, everything to the right of this one is 100% of the perlite. Then at here, everything will be 100% of the burnite. So we are at this point, which means it's 100% of the burnite. Therefore, for the problem of the C, you're going to have 100% of the burnite. Okay, so these are the things that you're going to do the homework, and you just follow the same procedure, and be careful when you read the time period in the log scale, and then you will be able to find how things will be transformed. The quench meaning you're going to freeze. Okay, the quench meaning you're going to freeze the composition that just before the quench. And the last thing that you will see in this chapter is they list a figure to show different kind of a transformation if you're doing a different rate of the cooling. If you start with the austenite, which is the one that we just show you at higher temperature, you do a slow cooling, that you are possible to get the perlite and also some poor eutectoid phase. If you do moderate cooling, you're going to have some burnite to show up. If you do quick quench, then most of them will become a austenite. We can also to change the property of the austenite by reheating the austenite such that we can have a tempered austenite. The material property will be different. As you can see, the material property is listed at this table. You can compare how strong or how soft these material are by looking at this table. And their microstructure is different. There's pictures of these this different microstructure to show you what they looks like. Which one is going to be stronger and which one will be weaker. If you look at the strengths, the austenite is the strong. Strong meaning it's brittle, okay? So strong doesn't mean it's better. So if you go to the top, it will be softer. So the bottom is stronger, the top is going to be softer. That means this is more ductile. this is going to be more brittle. Okay, and it depends on the temperature. So um, you do those homework can help you to understand how this transformation is, and we're going to have some discussion in the lab. So here is the end of our lecture for chapter 10.